So up until now, we have been studied the ISM itself, its cloud, dust and gas. But the ISM is not just sitting there. Stars constantly interact with it. They are born from it, and as they age, they return material back into it. So let's explore how stars give back gas and dust to the ISM, continuing the life cycle of matter in our galaxy. First, here we see Betelgeuse, a massive red supergiant. Surrounding the star is a bow shock, a curved shell where Betelgeuse's wind collides with the interstellar gas. So this structure tells us both about the star's powerful wind and the ISM it's moving through. And even stars like our sun expel material into space, but for massive stars like Betelgeuse, the wind is much stronger. So dust grains and gas are blown away, pushed by the pressure of the star's light. Now, infrared observations are crucial here because dust blocks visible light. But infrared light can pass through, letting us see the bow shock clearly. And aging stars lose mass as they near the end of their lives. So their outer layers made of hydrogen, helium and dust grains are expelled into the ISM. And dust forms from elements like carbon, oxygen and silicon condensing into tiny solid particles. So you can think of this as cosmic soot particles. And radiation from the star pushes this material outward, mixing it into the surrounding interstellar gas. And over time, this material becomes part of the ISM, ready to contribute to future star formation. So here on the image, look at the curved bow shock around Betelgeuse. So this is where the star's wind meets the ISM. A perfect example of stellar material returning to the interstellar medium. Now some stars end their lives in a dramatic supernova explosions. And these events eject huge amounts of hot gas and dust into the ISM. And now the shock waves from supernova compress surrounding gas, helping molecules to form. And they also stir up in the ISM, creating turbulence and shaping clouds. So this mixing spreads enriched material, heavy elements made in the star, throughout the ISM, increasing the chemical diversity of future generations of stars. So you can think of it as a cosmic recycling program. Stars give back the building blocks that will one day form new stars, planets, and even life. Alright, now that we have seen how aging stars return gas and dust to the ISM, let's look at what happens next. How this material collects and eventually forms new stars. So this is the beginning of the gas cycle. Now here you can see a visual of stars forming from a dense molecular cloud. Notice the dark dense gas and the dust in the background. That's the raw material from which stars are born. And the bright points are newborn stars starting to shine through the cloud. So these molecular clouds are called dense regions of the ISM where gas and dust have been compressed. And gravity and turbulence help these clouds gather into giant molecular clouds, often along the spiral arm of the galaxy. So the ISM is not uniform. Turbulence, shock waves and gravity compress regions of gas and dust into molecular clouds. And these giant molecular clouds can span hundreds of light years and contain hundreds of thousands of solar masses of materials. And these clouds are mostly invisible in optical light because dust blocks it. But infrared and radio observations reveal their structure clearly. Now look at the dark regions of the image again. These are dense molecular clouds where stars are beginning to form. And within these molecular clouds, gravity causes the densest regions to collapse, forming clusters of stars. Now, a single giant molecular cloud can form hundreds or even thousands of stars at once. And the most massive stars in these clusters are extremely hot and emit strong radiation, blowing gas outward and shaping the surrounding cloud. So, this explains why young star clusters often have a mix of star sizes and why massive stars influence their neighbors so strongly. And the cycle continues because massive stars live short lives, only a few millions of years, and end as supernova. Then the explosion blasts gas and dust back into the ISM, compressing nearby clouds and triggering more star formation. So these feedbacks keeps the ISM dynamic, recycling material and sustaining the gas star's gas cycle over billions of years. So molecular clouds collapse under gravity to form star clusters, and the most massive stars quickly return gas and dust to the ISM. And this is how matter cycles continuously, forming new generations of stars. Alright, now that we have seen how stars form from molecular clouds, let's look at the full picture, the gas stars gas cycle. So this cycle shows how matter moves from the ISM into stars and back again, continuously shaping our galaxy. Now we know stars form from the ISM, live out their lives and return some of their mass back to space. But some of the gas remains trapped in stellar remnants like white dwarfs, neutron stars or black holes. And that portion is effectively removed from the cycle. So most of the expelled gas and dust, however, mixes back into the ISM and becomes the material for the next generation of stars. Now first let's look at figure A and B. So here you can see a red giant star expelling gas and dust into its surroundings. And the glowing material in the image shows how the stellar winds pushes materials outwards. And this contributes to enriching the ISM and seeing future star formation. Now with each generation of stars, the chemical composition of the ISM changes. Hydrogen fuses into helium inside stars, and in massive stars, heavy elements like carbon, nitrogen and oxygen are produced. And when stars die, these heavy elements are returned to the ISM, enriching it and providing raw materials for new stars and planets. Now image C shows a supernova explosion. The expanding clouds of hot gas illustrate how heavy elements and energy are injected back into the ISM, stirring and compressing surrounding material, a key part of the cycle. So this gradual enrichment explains why later generation of stars, including the Sun, have more heavy elements than the earliest stars in the galaxy. Now this cycle is not just local. It affects the Milky Way as a whole. And over billions of years, the galaxy slowly uses up its star-forming gas. And the gas-star gas cycle drives the overall rate of star formation and chemical evolution of the galaxy, shaping the environment for future stars and planetary systems. Now image D shows how the gas and dust mix back into the ISM after supernova explosions and stellar winds. So you can see clouds of material spreading through space, ready to form the next generation of stars. So stars and the ISM are closely connected. Gas forms stars, stars return to enriched material, and new stars form again, completing the cycle. And this is the essence of the ISM's role in shaping our galaxy. Alright, now in this section, we explored the gas-stars gas cycle. So we saw how stars form from molecular clouds, how aging and dying stars return gas and dust into the ISM, and how supernova and stellar winds stir and enrich the medium. And this cycle drives the star formation, recycles material, and gradually changes the chemical composition of the galaxy over time. Alright, so with this we conclude section 3, and that wraps up chapter 10. So we have learned about the components of the interstellar medium, how we observe them, and how they interact with the stars to keep our galaxy alive and evolving. So let's go through a concise chapter summary, highlighting key ideas and observations about the ISM. So let's start with the basics of interstellar medium or ISM, the gas and dust that exists between stars in our galaxy. So most of this material is concentrated near the plane of the Milky Way, and it is extremely diffuse with only about 1 atom per cubic centimeter on average. And there are different types of nebula we can observe. H2 regions are clouds of gas ionized by nearby hot stars, which makes them glow a characteristic pink red. And reflection nebula scatter light from stars that are not hot enough to ionize the gas, giving them a blue color. Next, dark nebula blocks the light from background stars, and their irregular shapes show how turbulent the ISM can be. And the ISM is mostly gas, with dust making up only about 1% of its mass. And the dust dims and reddens starlight, and it also emits infrared radiation because of its large surface area. Next, the gas itself is cold and low density, which produces narrow absorption lines in stellar spectra. And in addition, low density gas can emit forbidden lines that we don't see in laboratory experiments. And neutral hydrogen produces the 21 centimeter radio line, which astronomers use to map the structure of our galaxy. So this section gave us an overview of what the ISM is, how it affects light, and the ways we observe it. Next, let's look at the main components of the interstellar medium. First, we have H1 clouds, which are regions of neutral hydrogen, and these clouds are cold, moderately dense, and typically a few tens of 100 parsecs across. And they coexist with the surrounding intercloud medium, which is hotter but much more tenuous. So the pressure balances out and both can exist stably. And next are molecular clouds, the densest and coldest regions of ISM. And these clouds are rich in molecules like molecular hydrogen and carbon monoxide, and their interiors are shielded from ultraviolet radiation. And giant molecular clouds can be hundreds of light years across and are the main sites where new stars form. And finally, we have coronal gas, extremely hot, low density gas produced by supernova explosions and winds from massive stars. So this gas fills large volumes and sometimes form super bubbles that can compress nearby clouds and trigger further star formation. And the sun itself lies inside the local bubble of coronal gas, and the boundary of our heliosphere interacts with this surrounding ISM. So in short, the ISM is a dynamic mix of cold, dense clouds, hot diffuse gas, and everything in between. So these components provide the raw material for star formation and the context for how stars interact with their surroundings. Now finally, we come to the gas stars gas cycle, which shows how the ISM and stars are intimately connected. So stars form from the densest regions of molecular clouds, and as they age, they return material back into the ISM through stellar winds or supernova explosions. And some of the mass stays locked in stellar remnants like white dwarfs, neutron stars, or black holes. But much of it cycles back into the interstellar medium, enriching it with heavier elements produced in the stars. And over time, hydrogen is converted into helium and other elements, gradually changing the chemical composition of the ISM. So this ongoing cycle drives new generations of star formation while slowly using up the galaxy's hydrogen fuel. and it is a self-sustaining process that links the starbirth, stellar evolution, and the chemical evolution of the Milky Way. Alright class, now with this we conclude the entire chapter. Now be sure to go through the review questions and practice problems to reinforce your understanding before moving on.